Welcome to CSAI Think Tinker Learn. This is part of my System Design Essential series. The goal here is to give you a solid mental model of a system design topic. We're breaking down the vector engine today, the hidden machinery that powers modern AI, recommendation engine, and image search. This is a concept first introduction to help you build your system design foundation quickly. If you want to see a deep dive on a special math or a case study on vector databases, let me know in the comments. You can also find the full technical articles on the site. These are GitHub pages which are available. The link is will be in the description. These videos are kept at a high level to provide the architecture big picture in a short duration. Let's explore the vector engine now. The fundamental problem with vector search is the brute force wall. In a flat index, every query vector is compared against every single stored vector. The computational cost is O n times d, where n is the number of vectors and d is the number of dimensions. At 1 billion vectors, a single query would take 18 seconds. Our real-time SLA for a modern app is usually under 100 milliseconds. We are off by 180x. This is a physical limit. You cannot simply buy your way out of this with better hardware. We need a fundamental shift in how we approach the search. To beat the brute force wall, we must sign the recall contract. We agree to the trade perfect accuracy for immense speed. This is approximate nearest neighbor search. Instead of finding the absolute best neighbor every time, we aim for a very close neighbor 1000 times faster. For most rack pipelines and recommendation system, a recall of 90 to 95%, meaning we find the true neighbor 9 out of 10 times, is indistinguishable from perfect to the end user. Accepting this approximation is the key that unlocks high-scale AI. Our first explored view is locality sensitive hashing, or LSH. Unlike standard hash functions that try to avoid collision, LSH functions are intentionally designed to create collisions for similar vectors. We project vectors onto random hyperplanes and record which side they land on as bits. However, LSH is largely dead for modern dense embeddings due to the curse of dimensionality. As dimension grow to 384 or 768, all points become roughly equidistant, and you need an exponential number of hash bits to maintain recall, leading to a memory and computation explosion. A more robust approach is the inverted file index. We divide our high dimensional space into regions using k-means clustering. Each region has a centroid. When we store a vector, we assign it to the nearest centroid. The system maintains an inverted list, a pointer from the centroid of all its resident vectors. At query time, we only scan around 1000 vectors inside the closest cell, completely ignoring the millions of vectors outside of it. This narrows the search space massively. But IVF has an edge problem. If a query vector lands near a cell border, the true nearest neighbor might actually be sitting just across the line in an adjacent cell. If we only check one cell, we miss it. To fix this, we turn up the nprobe dial. Setting nprobe to 5 means we search the 5 closest cells. This increases recall, but linearly decreases speed. It is important to note, if you set nprobe equal to the total number of cells, you've just turned your system back into a slow, exhaustive, flat index. Even if we solve for speed, we hit the memory wall. Storing 1 billion 128 dimensional vectors in float32 format takes up 512 GB of RAM. We must compress. We use product quantization. We split a large vector into smaller subvectors, train k-means on those subsegments, and encode them with the ID of the nearest centroid. We can turn a 512-byte vector into a 4-byte compressed code. This is a lossy compression, meaning we introduce quantization error, but it allows us to fit massive dataset into a local memory. In production, the workhorse is IVF-PQ combination. IVF handles the where to search routing to solve the speed bottleneck, and PQ handles the how to store protocol to solve the memory bottleneck. This is the dominant approach for billion scale deployments, offering 32x to 64x memory compression and sublinear search times. If you're building for massive scale, this combination is the architectural standard you must master. For the highest performance, we use HNSW, hierarchical, navigable, small world graphs. Think of it as 6 degrees of separation for vectors. We build a graph where nodes connect to their nearest neighbors across multiple layers. Search enters at a sparse top layer, takes long-range shortcut jumps to get close to the query region, and then descends through increasingly dense layers to refine the search. HNSW consistently achieves state-of-the-art recall versus latency because it navigates without checking rigid boundaries. However, there is a HNSW warning zone. First, memory bloat. HNSW consumes roughly 3 times the RAM of an equivalent IVF index because every node must store H pointers. Second, local minima. Greedy walks can get trapped in neighborhoods that look optimal locally but are globally wrong. We fix this by tuning parameters like M, which are max connections, EF construction, build quality, and EF search, which is the query depth, which can actually be tuned at runtime to balance your speed and accuracy needs. To define what close actually means, we use different distance metrics. Euclidean metrics measure straight line distance and is sensitive to magnitude. Cosine measures only the angle, ignoring magnitude. This is best for text embeddings. Inner product measures both direction and magnitude, making it ideal for recommendation relevance. A senior tip: normalize your embeddings to length 1 before insertion. This makes cosine and inner product mathematically equivalent, unlocking much faster hardware instruction on modern CPUs. It's important to distinguish between a library and a database. A library like FICE is the engine. It runs the raw math and algorithm in local memory. A true vector database like Pinecone, Milvus, or Qdran is the car built around that engine. A database adds metadata filtering, which is like a SQL-like predicate before and after the N and such. Persistence to disk, shard replication for 1 billion plus scale, and a real-time CRUD operation, so you can update data without rebuilding the whole index from scratch. Use this engine selection matrix for your next architecture review. If you need 100% recall and have a small data, use a flat index. If you need lightning fast latency but have limited RAM, IVF PQ is your best bet. If you need the absolute best recall to latency ratio and have the budget for RAM, HNSW is the gold standard. Never pick an engine based on what's trendy. Pick it based on the constraints of your recall, latency, and RAM targets. To wrap up, remember the senior vocab. Understand the curse of dimensionality. Measure your recall at K and look into disk KNN if you need to bypass RAM bloat. Never suggest a B tree for embeddings. Vector have no total ordering and require geometric proximity, not sorting. Now I have a question for you. Given the high memory cost of HNSW, would you prefer to pay for the RAM to get the extra 5 milliseconds of speed? Or would you use IVF PQ to save 80% on your cloud bill? Let me know your trade-off strategy in the comments. If you enjoyed this episode, please like, share, and subscribe to CSAI Think Tinker Learn. Check out the companion site for more essential. See you in the next one.